In our last video, we saw how water plays a critical role in the body through its use as a solvent, as well as its use in mediating interactions between our different biological molecules. Now, of course, another key role of water is as a reactant. We, of course, can see this in condensation reactions or hydrolysis reactions, but we also see this in, of course, our acid-base reactions. Now, one of the key components of water that allows it to be used in our acid-base reactions is the fact that our water actually ionizes by itself, right? So with any solution of water, we always have some amount of our water that's reacting to produce our protons and our hydroxide ions. Of course, those protons will associate with other water molecules to become our hydronium ions. So we don't actually have H plus generally sitting around by itself in our aqueous solutions. Now, of course, this H plus could then be donated as an acid to another receiving base. Or, of course, our hydroxide ion can act as a base and react with other acids and accept those protons. So any water-based solution can act as both an acid and a base. Now, in today's lecture, what we're going to do is we're going to go over kind of the acid-base reactions that can happen in water, and then review some of the details of acid and base reactions, such as our equilibrium constant. So that would be the Ka, pKa's, and then how that affects our buffer systems. Okay, so to start off, let's take a closer look at the ionization equilibrium for our water itself. So as we can see over here on the left, our water can react in an equilibrium to form our proton and our hydroxide ion, which of course makes our hydronium, as I just mentioned. If we look at the equilibrium constant for this reaction, so as always, our equilibrium constant is our product, so that's the H plus and the hydroxide ion over our reactants, which is our water, each raised to its stoichiometric coefficients, which in this case is 1 for each of our components. We can actually determine what this equilibrium constant is using our usual experimental approach. So it turns out it's 1.8 times 10 to the negative 16th at 25 degrees Celsius. Now, for water, the concentration of water within a solution of water is just dependent on what the density of water is. And this comes out to 55.5 molar. So if we take our 55.5 and multiply it by 1.8 times 10 to the negative 16th, we get the ion product of water, which we abbreviate as our Kw. So ion product of water is 1 times 10 to the negative 14th. And this is the quantity that we will usually use rather than this equilibrium constant value that I showed above. Now, of course, because this 1 times 10 to the negative 14th ion product of water, this is equal to our H plus and our hydroxide ion concentrations, right? Since we've multiplied our water concentration by the equilibrium constant. And so in pure water, we have equal amounts of H plus and OH minus, both equal to 10 to the negative 7th. That would be in pure neutral water. Now, of course, this ion product constant, these concentrations of H plus and OH minus in our pure water will relate directly to our pH scale. So, of course, as you should remember from general chemistry, pH is just the way that we normally express the H plus, or the hydronium ion concentration in solution. So we express it as a negative log, so we can easily show the wide ranges of H plus concentrations that we see in different acidic or basic solutions. So pH is equal to the negative log of H plus. Our Kw, as we just saw, is equal to 1 times 10 to the negative 14th. So if we take the negative log of this equation here, we can express this in terms of pH. Now remember, of course, when we have the logarithm of a product, that's the same as adding those two logarithms together. So negative log of H plus times OH minus becomes minus log H plus minus log OH minus equals 14, which is the negative log of 1 times 10 to the negative 14th. And this simplifies to pH, which is the negative log of the H plus, or the hydronium ion concentration, and plus the pOH, which is just the negative log of the hydroxide ion concentration. So both of these terms are coming directly from that equation above. So our pH and our pOH are both related, right? So we know that our neutral pH is normally pH 7. That would be when we have 1 times 10 to the negative 7th of our H plus ions, our hydronium ions. And at the same time, our pOH is kind of the inverse of our H plus concentration, right? Since the products always have to be equal to 1 times 10 to the negative 14th. So of course, if our pH is 7, our pOH also has to be 7, so that they're equal to 14. And that would correspond to that 1 times 10 to the negative 7th concentration of our hydroxide ions. So this is the scenario for pure water. And of course, as we change the pH or the pOH by adding different acid or basic compounds, both the pH and the pOH change inversely, right? So of course, if we raise our pH to 8, then our pOH has to lower to 6 in order for those both to still equal 14, based on our ion product constant for water. So of course, this leads naturally to our pH scale. So remember, the pH scale kind of shows the relative acidity or basicity of a given solution, right? So we have a pH 7 here in the middle. This is our neutral pH. And of course, as we go to lower pHs, we get more acidic. So we're strongly acidic if we have, say, pH 2 or lower, roughly. And we're strongly basic as we increase that pH to around the 12 to 14 region. Now, of course, we could also put a pOH scale on here at the same time. So our pOH, of course, would be 7 at the same time that our pH is 7. But our pOH would be 14 while our pH is 0, and our pOH would be 0 while our pH is 14. Again, there's that inverse relationship that we just saw in that previous equation, where our pH and our pOH always have to make 14 if they're combined together. Okay, so how do we actually adjust the pH or the pOH of a given solution? How does this affect our biological molecules within that solution? Well, of course, as we know, this occurs through acid-base reactions as we add either acids or bases to our water solution, right? So if we add a weak acid, such as our acetic acid shown up here, so acetic acid is one of our carboxylic acids that we learned about in organic chemistry. And of course, that carboxylic acid functional group is weakly acidic, so it reacts with water and it creates some of our conjugate base here, the carboxylate, as well as our conjugate acid of our hydronium ion. Now, of course, this hydronium ion will contribute directly towards changing our pH. So our pH will decrease as we produce more of that hydronium ion and make our solution more acidic. Now, in the case of a weak acid, like our acetic acid here, this reaction is not going to go to completion, right? So we have an equilibrium constant, shown right here, that will determine how much of our acetic acid reacts to, of course, change our pH through producing that hydronium ion. The extent of this dissociation, the reaction of our acetic acid, is determined by the Ka, the acid dissociation constant of our acetic acid here. So the Ka is just the specific name of the equilibrium constant for this reaction of a weak acid. So as usual, we have our products on the top over our reactant on the bottom. Of course, remember, normally water isn't shown in aqueous reactions like this because it's the solvent. The Ka in this case is 1.74 times 10 to the negative fifth, and that just tells us the relative ratio of how much of our acetic acid reacts versus how much of it stays as our weak acid within a given solution. Now, the value of that Ka is it tells us how much our acid is actually going to react and then change our pH. So in this case, we're adding 0.1 moles of acetic acid into 1 liter of water. So that's going to be a concentration of 0.1 over 1 liter. And we want to know how that's going to affect our pH. Notice we have an assumption here that the only source of H plus is going to be our weak acid. We usually ignore the initial H plus of 1 times 10 to the negative seventh within our solution of water, just because it's so small compared to the H plus that's produced in this reaction. So what we're going to need to do here is set up an ice table in order to show us how much of our acid is going to react to produce the H plus ions. So we have initially that 0.1 molar that I just showed you before, and we're going to assume that some amount of it is going to react. So X is the amount that reacts. And of course, at this point, we don't know exactly how much is going to react, so we're representing it as an unknown. So some amount of our acetic acid is going to react, and it's going to produce an equal amount of our acetate and our H plus. So X is our change in this case. Our initial value was the 0.1, and these will be our final values at equilibrium. So this is the E part of our ice table. So now we can place these into our equilibrium expression. So X are our product concentrations. 0.1 minus X is our reactant concentrations. So we can set up our equilibrium expression. And of course, we know our equilibrium constant in this case. I gave that to you on the previous slide. And we can then solve for X to calculate exactly how much H plus ions are produced. So I would multiply both sides by 0.1 minus X. So that gives me 1.74 times 10 to the negative 6. That's 0.1 times 1.74 times 10 to the negative fifth, minus 1.74 times 10 to the negative fifth X, equaling X squared. I rearrange it so all my X terms are on the left side. So now I have X squared plus 1.74 minus 1.74 times 10 to the negative 6. And then, of course, at this point, our equation takes the form of a quadratic equation with our term right here, 1 acting as A, our 1.74 times 10 to the negative fifth acts as B, and our C term is 1.74 times 10 to the negative 6. So if we plug that all into our quadratic equation, we should then calculate X equals 0.001310. That, of course, would be equal to our H plus concentration. And so we can then take the negative log of that to calculate our pH as 2.883. So this is the more exact way of calculating our pH when we're adding a specific amount of a weak acid. Of course, we could also add in a small amount of H plus initially from our water, right? But you'll notice at this point we have 1 times 10 to the negative third H plus compared to 1 times 10 to the negative seventh, right? So the amount of H plus initially in our water is insignificant compared to the new amount that forms in this reaction. Now, in many cases for weak acids, we can actually simplify our calculation here by assuming that the amount of our dissociated species, so that's our acetate here, is much less than the amount of our undissociated acid, right? So we're assuming that we produce much less of our acetate compared to our original acetic acid, right? We're saying that the equilibrium actually favors our reactants, and we're not going to have a large amount of our products formed. So in this scenario, we're going to have a very similar equation as before. We're looking at our initial amount of our reactant, and then we're subtracting some amount that's reacting as we produce our products. But with our added assumption, we can now change this and say that our initial amount, or our final amount rather, of our weak acid is still going to be very close to 0.1, right? So instead of using 0.1 minus x in our equation, we can say, okay, x is going to be really small compared to 0.1, and so we can just say 0.1 here, right? So now at this point, when we put this in our equilibrium expression, we have x times x over 0.1 as the concentrations of our acetate, our H+, and our acetic acid at equilibrium. We can rearrange this. So this becomes x squared equals 1.74 times 10 to the negative 6. Of course, this would be in units of molar. And we just take the square root here in order to solve for x. So when we take the square root, we get x equals 0.00132. Take the negative log of x, and we get our pH as 2.880. So notice with this assumption, we do get a slightly different pH value. Previously, we had 2.883. Now we have 2.880. So there is a slight inaccuracy added by that extra assumption that we made here. But for the most part, it's still fairly accurate, right? So it's accurate down to the hundredths place of our pH, right? So we calculated 2.883 before. Now it's 2.880. In general, this assumption is going to be accurate whenever we have a very small Ka, right? A small Ka means that not much of our acid is going to react. So again, the X value is likely to be much less than our initial amount of acid. Now, of course, the other thing you can do to check this assumption is actually take this X value that you calculate and subtract it from 0.1, right? So if we take 0.1 and subtract 0.00132, we get 0.09868, which of course is still very close to 0.1, right? So you can see, okay, our value of 0.1 does decrease slightly, but not all that significantly to our created acid here, our created acetate rather. So these sorts of calculations can show us how the addition of weak acids will affect the pH of our aqueous-based solutions. Now, of course, this is very important in biochemistry because we have a lot of different organic compounds, like our acetic acid here, that act as weak acids or weak bases. And we need to know how they affect the pH of the solutions within our body as we're adding in these different biological molecules. And of course, in the same way, this will also show us how the pH, right, that's our H+ concentration over here, will affect the relative state of our biological molecules, right? So if we have a very low pH, then we're going to drive this equilibrium to the left and produce more of our protonated form of a specific biological molecule. If we have a very high pH, so a low concentration of H+, then we're going to be more likely to deprotonate our weak acid biological molecules and form the deprotonated conjugate base form. So you can look at this in two different ways. You can look at it as a way to calculate how the pH will change as we add certain weak acid or weak base biological molecules, or we can look at it as a way to see how the pH will affect the relative ratio of that conjugate base form versus the weak acid form of our biological molecules. Now, one of the ways that we can easily look at the ratio between our conjugate acid and our conjugate base form is actually using pKa's instead of our Ka for our equilibrium constant here. So the pKa, of course, is just the negative log of our Ka. And the nice thing about our pKa is the pKa essentially corresponds to the pH at which we see that particular weak acid starting to react and turn into its conjugate base, right? So depending on what pKa you have for our given weak acid or weak base, it will tend to deprotonate at a different point within our pH scale, right? So here's the acetic acid that we looked at here. Its pKa comes out to 4.76, which means that around pKa 4.76, or around pH 4.76 is going to be where it tends to change from the protonated form to the deprotonated form. Something with a higher pKa, like our ammonium ion here, will tend to get more deprotonated at higher pH values. Now, of course, the easiest way to illustrate these sort of deprotonation events is with a titration curve. So here we have a titration curve for our acetic acid. So of course, on our x-axis, we have the amount of base added. So we're adding base in order to deprotonate our acetic acid from the weak acid form to the conjugate base form. Of course, as we add that base, we're also changing the pH. So initially, we're starting with pure acetic acid, which is going to have a relatively low pH, right? Because we have a very strong, a very high concentration of that weak acid within our solution. As we add our base, so if we add half as much of our strong base as we have of our weak acid, we're going to react half of our acetic acid to our conjugate base. So we'll have exactly half of our weak acid and half of our conjugate base right here in the middle. Now this point is always going to be equal to our pKa. So notice that our pH point over here on the y-axis is slightly below 5 at that 4.76 pH, where we hit our pKa. Right? So the pKa tells us the pH at which our weak acid and our conjugate base concentrations are equal. Now, as we continue to add base, we're going to produce more and more of our conjugate base form. And so once we've added as much base as we have our weak acid, we'll have converted essentially all of our weak acid into that conjugate base form. So that, of course, will be up here at a very high pH. Now, again, for any given weak acid, we'll see the same kind of titration behavior, right? It's always going to start in the acid form at low pH, and then as we add strong base, we can slowly convert it over into the conjugate base form. We'll always get this midpoint where we have our conjugate base and our weak acid concentrations being equal at the pH equal to our pKa, right? Notice for each of these, the pH over here on the y-axis is corresponding to the pKa of that specific weak acid. And of course, as we continue to add our strong base, we can eventually convert it over into our conjugate base form. So these sort of titration curves, right, they can show us very clearly what that relative ratio will be of our weak acid to our conjugate base at a specific pH value. They also show us how that pKa relates to that ratio between our weak acid and our conjugate base. Now, from a biological standpoint, this is incredibly important because, again, as we're changing this, we're actually changing the charge of these molecules. And that's going to change the kind of biological interactions that these molecules might have, right? They go from being neutral compounds, in the case of our acetic acid, to something that's negatively charged and now can participate in ionic interactions. Or in the case of ammonium, we start with a positive charge where we can participate in ionic interactions, and we end neutral, where now we can't participate in those ionic interactions. Now, the titration behavior of our weak acid will, of course, also relate to its ability to act as a buffer. So, of course, the basic definition of a buffer is something that resists a change in pH. And as we know from general chemistry, a buffer is made by combining a weak acid with its conjugate base. So that the weak acid then can react with any added base, whereas the conjugate base can react with any acid, and it can resist those large changes in pH. So as we just saw on our titration curves, when the pH is equal to our pKa, there's a 50-50 mixture of our acid and the conjugate base form of our particular compound. This is also the point where we say that we have the greatest buffering capacity for our acid-base mixture, right? So at that point, we have an equal amount of either our acid and conjugate base, and they can both be available then to resist any acids or bases that are added. As a general rule, we tend to say that we lose our capacity to act as a buffer. We lose our buffering capacity when our pH differs from the pKa by more than 1 pH unit. So if we go back to our titration curve, the buffering region is actually marked here in blue. So this is our pKa plus 1. So that's 5.76, and minus 1 to 3.76. This is the region where we tend to see the smallest pH change, right? Our pH, of course, is over here on the y-axis. And notice in this region here in blue, we have a huge change in our base concentration, right? The amount of base that we've added. So 80% of our base is added within this blue region here. And as we're adding it, our pH has a very small change, right? We go from 3.76 to 5.76 at the full range of this 80% of our strong base that we've added, right? And it's these little regions at either end where our buffering capacity is lost and we see the largest pH change, right? So in this initial 10% of our base addition, we go from pH 1 to almost pH 4, right? So leap of 4 pH units with just a 10% increase in the amount of base that we've added. And again, we see kind of the same scenario over here, another 10% increase, and we go from roughly 6 to somewhere around 9 to 10. Again, roughly 3 to 4 pH units increase with just that 10% addition. Again, compare that to the 80% of our base that just had a 2 pH unit increase, right? So that shows the resistance of our buffer within this middle buffering region as that base is reacting with our conjugate acid here instead of having a significant effect on our pH. Now, when we're working with buffers in biochemistry, we commonly use the Henderson-Hasselbalch equation to allow us to quickly calculate the pH for a given ratio of our buffering components. So I want to quickly show you where the Henderson-Hasselbalch equation comes from, and then how we can apply that to easily calculate the pH within a given buffer system. So as we know for any weak acid, right, we have our basic acid-base equation over here with that weak acid dissociating to produce our hydronium ions and our conjugate base. This also relates to our Ka as our equilibrium expression with those products over reactants. We can rearrange this to isolate our H plus concentration because, of course, that will relate directly to the pH. So here we're just multiplying both sides by HA and then dividing both sides by our A minus. So multiply here in order to cancel out on the right side and put those on the left side with our Ka. Now at this point, we can take the negative log of both sides. So we get negative log of H plus. That, of course, is equal to pH. We get negative log of Ka. That, of course, is equal to pKa. And then we have negative log of HA over A minus. Now remember, of course, negative signs with logarithms can be switched around if we invert our ratio here. So this is actually equal to the positive log of A minus over HA. Right, so I switched my ratio here upside down and switched the sign of my logarithm. And this gives me my Henderson-Hausbach equation. So the pH is equal to pKa plus the log of A minus, our conjugate base, over HA, our weak acid. And again, this Henderson-Hausbach equation makes a great, easy way to calculate the pH if we know the pKa of our buffering component and if we know the relative concentrations of our base and our acid. Now, we do want to mention that this, of course, is only true at equilibrium, right? So you do want to be careful. You can't just apply the Henderson-Hausbach equation to any scenario. You have to make sure that you've used your proper ICE tables to calculate that equilibrium concentration of conjugate base and weak acid before you apply this Henderson-Hausbach equation. So here's what an equation might look like. So we have a buffer that has 0.1 molar acetic acid and 0.05 molar of sodium acetate, which of course is our conjugate base. We want to calculate what the final pH is of our buffer. So this is a relatively straightforward application, right? We have the pKa, we have the concentrations of our conjugate base and weak acid, and so we can put these directly into our Henderson-Hausbach equation, right? Henderson-Hausbach is pH equals pKa plus the log of our conjugate base over our weak acid. So we have the 0.05 over the 0.1 and our 4.76 for that pKa. And then you can simply put this into your calculator and calculate your final buffer pH as 4.45. Now, one of the things, of course, that it's always good to check here is just to make sure that your answer makes sense according to your given concentrations of your weak acid and your conjugate base, right? So as we know from our titration curve, when the weak acid concentration is higher, we should get a lower pH. When the conjugate base concentration is higher, we should get a higher pH. And if they're equal to each other, our pH should equal to pKa. Right, so right now HA is greater than A minus, and so we know that our pH should be lower than 4.76, which of course is what we see. Within our body, it's incredibly important to maintain the correct pH. So this is important for essentially all of our biochemical processes that we see within cells, as well as within our greater body systems. A lot of the different reactions that we have within our body are catalyzed by specific enzymes. These enzymes will have optimal pH values that if the pH varies too far from those, the enzyme will no longer function. It will also, of course, as I said, it affects the charge of our compounds as they're either protonated or deprotonated, which can also then affect the solubility, right? So we might have our solubility increasing as we become deprotonated and increase that charge. It also changes what our hydrogen bonding looks like, right? So after you've deprotonated a carboxylic acid, you no longer have that hydrogen bond donor of the OH there. So all of our biological processes are affected by that ratio of weak acid to conjugate base. So it's actually very important to maintain a specific pH within the body so that we're not just constantly changing the charge and the solubility and as well as the rates of our reactions. So an example of this, of course, is shown down here. We see this a specific amino acid of histidine. So this is present in a lot of the different enzymes or the proteins within our body. And we see that it can easily react as an acid, and it can give up that positive charge, which can then alter how that enzyme or protein behaves in our body. As an example of how pH affects our enzyme activity, this graph here shows 3 different enzymes and their relative activity versus pH. All right, so you'll notice they each have different specific pH values that they like to work at. Right, so pepsin likes very low pH values around 1.5. Our trypsin here in red likes more neutral pH values. This is between 6 to 7 for the optimal pH. And our alkaline phosphatase prefers actually a higher pH around 8 to 9. And these optimal pHs also correspond to where these enzymes tend to be active, right? So pepsin is more active in the stomach where it's strongly acidic. Alkaline phosphatase can be more active in intestines where it tends to be a little bit more basic, whereas of course the rest of our body tends to be more in that kind of neutral pH range right around pH 7. So changes in pH can be very damaging to the body. If we have scenarios where we're increasing the amount of acids that we have in our body, this can cause acidosis or a lowering of our blood pH. So this can occur through various metabolic processes. If we're producing lots of acids, such as these compounds shown here, these are compounds that can accumulate in diabetes to create acidosis. And then again, that low blood pH affects all those reactions and affects the charge and the interactions of our various biological molecules. Of course, acidosis can also occur through production of lactic acid if you have excessive anaerobic exercise. So that can also create some amount of acidosis as you're creating large amounts of this weakly acidic lactic acid. Now, of course, the counterpoint can also occur where you can have alkalosis if you have too many basic compounds produced and then increase your blood pH. So we're always kind of trying to keep this balance between high and low pH in order to avoid those changes in our enzyme activity or in the charge of our biomolecules. So we tend to use a wide range of different buffer systems in order to help prevent those pH changes. In biological labs, we tend to use a variety of different sulfonic acid-based buffer systems. So these are all referred to based on different abbreviations generally. We have HAPES, PIPES, and CHES. These each have different pKa values that allow them to work as buffer systems for varying pH ranges. Here's an example of one of those buffer structures. This would be HAPES here. Again, these are just a variety of different weak acids that you can use to try to help control that pH value based on the pKa value of your buffer. In our biological systems, we use a little bit different buffers. So one of the most common buffers is a phosphate-based buffer. So phosphate is a triprotic acid. The most relevant pKa is this one at 6.86 as we go from our H2PO4 to HPO4 2-. We also, of course, use our carbonic acid-based buffer system. So this is the most important buffer for the blood, where we have this buffering reaction between our carbonic acid and our bicarbonate that's used to help balance our pH within the blood. Now, the bicarbonate buffer system is a little bit more complicated because it's also affected by the concentration of our carbon dioxide, right? So dissolved carbon dioxide can react with water to produce extra carbonic acid, which would then lower the pH slightly. So in this case, the amount of carbon dioxide that we're breathing out or is dissolving in our bloodstream can actually affect that buffering and the pH there as well. So in this lecture, we've seen how the reactions of weak acids and bases can affect the pH within our water-based biological systems. We also see how buffers can be used to control that pH. We'll see this again and again throughout our study of biochemistry, that pH is really critical for our body's behavior. And we always kind of see these balanced reactions of things getting protonated or deprotonated, and then that slightly changing how things are interacting or behaving within our body. So again, this is one of the critical roles of water in kind of mediating these different acid-base reactions.